This is Ideas Worth Exploring by Mark MacDonald.
Imagine this. Pretend you're making a new planet from scratch, and you want to know how the climate and weather patterns will be affected by each new feature you add. We're going to start with a featureless sphere, then add in mountains, water, plants, and snow. Then we'll sprinkle some humans on and let them build cities to see what that does. And finally, we'll make the planet rotate and see what kind of chaos that creates. So let's start making a planet. This episode is about climate science, where climate means the long-term weather patterns of an area, if it tends to be hot or dry or snowy or what. In the near future, I intend to do another episode about climate change, but that's not today. Also in the future, I'd like to do another episode about specific weather phenomena, like tornadoes and hurricanes, but that's also not today. Please let me know if either of those things interests you. I'd love to get feedback about that. So, time to make a planet. You begin with a flat, featureless surface. But before you add anything to it, you have a decision to make. What shape should you make your planet in? You decide that because you love baseball so much, you're going to shape your planet like a ball. But, right off the bat, you see that this creates an interesting temperature pattern. The middle surface of the ball, around the equator, gets much hotter than the top and bottom. What's up with that? Feature number 1, latitude. On any planet shaped like a sphere, temperature generally changes with latitude. It's pretty common to think that this is because the poles are farther away from the sun than the equator is. But that's not the reason. The extra distance from the sun is way too small to make any kind of noticeable difference. The actual answer is angles. Closer to the equator, sunlight hits straight on, while as you move up in latitude, the Earth curves away and the sunlight strikes the surface at an angle, which spreads out the solar energy more. You can test this yourself. Shine a flashlight on a table, straight on. Then shine it at an angle. You'll see that as the angle increases, the light gets spread out over a larger area, so the light looks less bright. The light energy gets more spread out as the angle gets steeper. That's the main reason why temperature goes down as you get closer to the poles. It's all about them angles. Interestingly, the angle of sunlight also matters on a smaller scale. A slope where sunlight shines straight down on it will have different plants from a slope that is angled away from the sun. And according to some textbook I found online, Chicago's northern suburbs run a degree or two cooler than its southern suburbs because of the angle of the sunlight that reaches them. I don't know whether this last one was true or not, but it would be cool if it was. Okay, so your new planet is a sphere, and now you know some of what that entails. But a featureless sphere is boring, so you decide to add some mountains to it. You immediately notice that as you get higher up on a mountain, the air gets cooler. What's up with that? On top of the mountains, you're closer to the sun, so shouldn't it be warmer? Nope. Once again, that difference in distance is small enough to be completely negligible. Feature number 2, altitude. The answer to why it gets cooler as you go up in elevation needs a little bit of physics to understand. It goes like this. Air doesn't get heated directly by the sun very much. Mostly it gets heated by the ground. So, air near the ground gets warm. Warm air tends to rise. When it rises to a higher elevation, there's less air pressure, which makes sense because as you go up, there's less air above you pushing down. So, when air rises, the lower air pressure makes it expand. And finally, here's where the interesting physics is. When the rising air expands, it cools off because of something called adiabatic cooling. What does adiabatic mean? To me, it brings to mind 80 diabetic bats in my attic. Adiabatic. But that's not helpful at all, sorry. What adiabatic cooling actually means is that a gas cools down when it expands, even if there's no heat transfer going on. So, imagine those 80 bats all have the chills. This cooling happens because, to expand, the air has to move the surrounding air out of the way, which takes energy. The energy comes from the air's temperature. The temperature energy is used to do work so the air can expand, and this makes the air cool down. You can actually see adiabatic cooling in action if you have a 2-liter soda bottle a rubber stopper, and a bike pump. Just put water or rubbing alcohol in the bottle, use the bike pump to put the bottle under a lot of pressure, and then pull the stopper out quickly. You'll see the water in the bottle suddenly condense and form a cloud inside the bottle. That's because the sudden decrease in pressure cools the air enough to make the water suddenly condense into a cloud. But be careful with this experiment. A little over a year ago, a BYU physics professor tried it with a glass flask, but he let the pressure get too high, and the flask exploded and hurt him and nicked a couple of the students in the front row of the class. But don't worry, everyone recovered, and I was told that because of the incident, the deadline for the test was extended. So, to recap, it's cooler at higher elevations because the air pressure is lower, and when air moves to a lower pressure, it expands, which makes the diabetic bats cool it down. Sorry, I meant that it cools down due to adiabatic cooling. The temperature energy is spent doing work on its surroundings. So, that's how elevation affects temperature. There's also another thing that mountains do that affects the weather, other than the temperature thing. Mountains block winds and rain clouds from getting past, which is called the rain shadow effect. As air goes up over the mountain, it cools off, making the water in it condense into clouds. So on the side of a mountain closer to the ocean, you'll get more rain, while on the other side, it can be dry, sometimes even a desert. That's the rain shadow effect. Okay, so you have a bumpy sphere for a planet now, but you feel like it needs some stuff on it. So you decide that, first off, you want to add water. Splish splash, let's see what it does. Feature number 3, water. Water has a temperature moderating effect on the area around it. You know how after you boil water, it can take almost an hour to cool back to room temperature? But the pot that you boiled it in cools off real quick after you pour the water out. That's because water is really good at holding a lot of heat energy. We say that it has a high specific heat. Water is much better than land at holding on to energy. This means that it heats up more slowly and also cools down more slowly. So if you're near a body of water, it'll generally be cooler in the summer and warmer in the winter than it would be far away from the water, because of how well water holds on to heat energy. Also, if you're near a large body of water, like the ocean, it'll probably rain more. Okay, water has a temperature moderating effect. Now that we have water, we can add other things to our planet too. Trees, plants, ice, and snow. Feature number 4, vegetation. Let's start with trees and plants. Plants collect water from the ground and pull it up into themselves, where some of it escapes through evaporation. When water evaporates from plants, it's called transpiration. This cools the plant and the air around it a little bit, because some heat energy from the air goes into evaporating the water. So trees and plants help cool the area around them because of transpiration. They also provide nice shade, I might add. Feature number 5, ice and snow. So plants cool the air. You know what else cools the air? Ice and snow. But not because they're cold. Or I should say, not just because they're cold. Ice and snow are kind of shiny, which is important. I need to introduce you to a new word. Albedo. Albedo means the proportion of light that gets reflected from a surface. A higher albedo means more sunlight gets reflected back into the sky instead of heating up the ground. Ice and snow have a very high albedo. In fact, ice does such a good job of reflecting solar energy that it can make weird things happen. When ice covers a large area, that area gets cooler because it reflects more sunlight, which lets more ice cover the area in a vicious cycle. This is what happens during ice ages. The opposite also happens though. If ice melts, then the area absorbs more sunlight, which can make more ice melt, another vicious cycle. So ice can multiply the effects of small changes in temperature and have a big impact on the Earth's climate, which is why ice ages are a thing. But that's a whole nother topic, so for now I'll just say that ice is good at reflecting sunlight, and that cools the area around it. I'm going to move on now, but I'll admit that I'm skipping some things. Humidity and cloud formation are both very important for understanding climate science. There are also some really interesting things about what happens in deserts, but I'm ready to move on. When you build your own planet, you'll just have to experiment with those things for yourself. Feature number the next. Cities. Okay, now it gets exciting, because I'm going to sprinkle some humans onto our planet. Humans do all sorts of interesting things. Some of those things deserve a whole episode of their own. Cough, cough, climate change. And I'll be sure to make that happen soon. But for now, we're going to focus on just one thing that humans do. Humans build cities. And cities, with their asphalt and concrete and tall buildings, tend to be built in a way that makes them really hot. There's this thing called the urban heat island effect, where cities tend to have an average temperature of up to 7 degrees Fahrenheit warmer than the surrounding area during the day, and up to 5 degrees at night. That's a little upsetting. At certain times of day and in certain places, the difference can be as much as 22 degrees. There's a bunch of reasons why it is so much hotter in cities, which I'm going to discuss one by one. 1. Vegetation. Since cities tend to have less vegetation than the surrounding area, they tend to be warmer because they miss out on the cooling effects of trees and plants due to transpiration that I mentioned earlier. Also, fewer trees means less shade. 2. Geometry. Tall buildings and narrow streets can form what's called an urban canyon, which can block wind flow, trapping the heat in the city. Tall buildings and narrow streets can also affect how light bounces around, trapping heat in the materials the buildings are made of. I still don't completely understand why, but according to studies, having tall buildings is one of the biggest factors that contributes to the heat island effect. 3. Heat sources. Humans create heat whenever we drive a car or use electricity. For example, air conditioning. In one study, it was found that air conditioning can increase the temperature outside by almost 2 degrees Fahrenheit during the nighttime. If you've ever wondered if we can reverse climate change just by building a bunch of really big air conditioners, I'm sorry to say, no. To put cold air inside your house, an air conditioner has to make even more hot air outside your house, and when everyone does that, it's enough to raise the temperature of the city by a noticeable amount. But only during the night. During the day, the increase is negligible compared to the hot sun. But still, it's a vicious cycle. Using air conditioning at night raises nighttime temperature, which makes more people use air conditioning at night. And 4. Albedo. You know what doesn't reflect a lot of light? Asphalt. So building roads and parking lots makes the city hotter, because more light energy gets trapped. Boo! Parking lots! Boo! You make the city too hot! But parking lots aren't the only culprit. Buildings and houses can also contribute a little bit to trapping more heat than they could. But, if you own a house, there are 2 things you can do to lower your albedo, if that's something you care about. If you're thinking of replacing your roof anytime soon, you could consider using a cool roof, which uses shingles that reflect more sunlight, especially in the invisible infrared region. It isn't that much more expensive than normal shingles, and if you live in a warm area, it can cool your house and maybe even save you money on air conditioning. And also, if you have a cool roof, your neighbors will think you're cool. And the other thing, painting your house white could also help. A 2021 study showed that an ultra-white paint could reduce or even eliminate your need for air conditioning. It looks like this specific ultra-white paint is still not available to the public, but normal white paint, or even other light colors, can help as well. Oh, and bonus number 4.5, asphalt and concrete. It's not just albedo that makes asphalt and concrete heat a city. Asphalt and concrete can make it so groundwater can't get to the surface to evaporate, so cities miss out on a lot of the temperature moderating effects of water. In summary, there are many things that make cities hotter than the countryside, and if you're concerned about them, you can encourage city planners to take them into account. Support efforts to plant more plants in the city, especially in low-income areas that need it more, and try to make your houses more reflecty. So, that's the urban heat island effect that makes cities hotter than their surroundings. Now let's go back to our original endeavor of building a planet. Remember that? Now we have a planet that's a sphere, covered in mountains, water, trees, ice, snow, and cities. Next, we're going to make the planet spin. And that's going to do all sorts of weird things to the winds and the ocean currents. Feature number, I lost track by now. Wind patterns. On a rotating planet, air tends to turn to the side instead of going in a straight line. And it happens for a very strange reason. The actor who played Wesley in The Princess Bride waves his hands and makes the winds bend. It's called the Coriolis effect. What's that? I'm now being told that that's not actually how it happens, that there is no actor involved, and that it's really called the Coriolis effect. Sorry for the confusion. Okay, here's the actual reason air currents don't like to travel in a straight line. It's about rotation. You have a planet that's mostly spherical, and you make it spin. For the sake of argument, pretend we're talking about Earth. In case you didn't realize, Earth is spinning. But since Earth is spherical, different parts of the Earth move at different speeds. Think of it like this. The Earth completes one rotation in 24 hours. If you're standing 1 foot away from the North Pole, then that means you travel in a circle of about 6 feet in circumference in that 24 hours, which adds up to about 0.00005 miles per hour. However, if you're standing on the equator instead, then in those 24 hours, you traveled the circumference of the entire planet, 25,000 miles long, which adds up to about 1,040 miles per hour. Just by standing still on the equator, you're going almost as fast as a bullet. You don't feel it because people don't feel motion, people feel acceleration. And the acceleration needed to get you moving that fast over a 24-hour period is small enough that you can't feel it. If the Earth was spinning faster, it would be fast enough to feel. For example, if Earth was spinning so fast that a day only lasted about 90 minutes instead of 24 hours, then things at the equator would start flying off into space. But it's actually not spinning that fast, and so it's slow enough that you don't really feel it. But anyway, equator moving fast, North Pole moving slow, what this means is that if you had a teleportation power, and you teleported from the equator to the North Pole, then you'd better hope that your power knows how to adjust for the change in velocity, or else you'll arrive at your destination traveling twice as fast as a jet airplane. Because different parts of the Earth move at different speeds, this creates what's called the Coriolis effect. Recall that the Earth spins counterclockwise when you look at it from the top, or left to right when you look at it from the side. When a parcel of air starts at the equator and moves north, it's still going at equator speed, which from the ground makes it look like the wind turned to the right. And this happens in general. Air tends to move to the right in the northern hemisphere because of the Coriolis effect, because different parts of the Earth travel at different speeds, because that's how a rotating ball works. So, in the northern hemisphere, air moving north will bend to the east, and air moving south will bend to the west. If the Earth were spinning the other way, you would reverse those directions. For the pedants out there, the Coriolis effect is actually more than that. It creates a force that acts 90 degrees to your direction of motion, even if you're not going north or south. But that requires a little more background, and I'm all backgrounded out right now. So let me just say, there's more to the Coriolis force than the intuitive explanation I just gave would suggest, and if you're interested, feel free to research it more on your own. One last thing, or two, depending on how much you like counting. The Coriolis effect is the reason hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern. It's also the reason people will claim that toilets flush counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. But that one is false. That doesn't actually happen. So, when you decide which way you want your planet to spin, you're also choosing which way you want your hurricanes to spin, but toilet flushes depend on the design of the toilet, not the planet. Okay, now we're going to switch gears and talk about something else. Then we're going to add the Coriolis effect back in. Okay? I'm going to pretend you said okay and move forward. The something else is called circulation cells. Air and water have to move in a closed loop, or else you'd have all the water or air building up in one place. These loops are wind patterns and ocean currents. I'm going to talk about one of the big air loops, called a Hadley cell for you trivia nerds. What you need to know is this. Hot air rises. And you know where it's really hot? The equator. Near the equator, where you get the most solar energy, the air likes to rise. Then it travels north and south, and comes down somewhere far away, and then travels back along the surface to close the loop. That's why there are usually strong surface winds blowing towards the equator. But right at the equator, the wind blows mostly straight up, and wind blowing straight up can't push a ship. So sometimes sailing ships would get stuck there for weeks. Sailors called this area around the equator the doldrums. There are also two more cells, closed loops of wind that make the air move over long distances. There's one cell near the poles, and one in between the other two, over the US and Europe and parts of northern Asia. The number of cells you get depends on the size of your planet and the speed of rotation. Jupiter has 8 compared to Earth's 3, and that's what gives Jupiter its stripes. Okay, now add the Coriolis effect back in. Near the equator, in the northern hemisphere, the surface winds try to blow south because of the circulation cell I just told you about. But, if you're spinning the same direction as Earth, the Coriolis force makes these north to south winds turn more westward. This produces a strong wind that blows from east to west across the ocean nearest to the equator. These are called the trade winds, because they're what sailors use to carry their ships across the sea to do trade. As for the two other circulation cells on Earth, the one near the poles causes surface winds to blow from east to west, and the one in between, which circulates the opposite direction of the other two, causes surface winds to blow mostly from west to east, which is the reason storms tend to move across the US from west to east. Oh, and I'll also mention in passing that when two cells meet, it forms a jet stream, a tight stream of fast winds that flow west to east and make your flights sometimes arrive quicker than expected. But I don't really want to get into jet streams right now, so let's go back to trade winds. For everything up to this point, I've tried to be general so that it applies to any planet you're trying to build. But for the next little bit, I want to specifically focus on Earth, because there's a little thing that happens that you might want to avoid. El Niño. Dun dun dun! In the Pacific Ocean, the trade winds blow warm water across the ocean and leave it off the coast of Asia and Australia. Due to the warm trade winds, the sea surface is normally about 1.5 feet higher and 13 degrees Fahrenheit warmer in Indonesia on the west coast than in Ecuador on the east side of the ocean. So, the trade winds move more warm water to the west of the ocean and leave cold water nearer to the surface on the east of the ocean. The warm water to the west makes the air rise, and the cold water to the east makes the air sink, which makes a loop of air that, near the surface, blows from east to west and reinforces the trade winds. Why are the trade winds so strong? Because the warmest water is in the west. Why is the warmest water in the west? Because the trade winds are so strong. It's a fragile feedback, which can easily be disrupted. When this feedback is disrupted and the trade winds weaken, it creates an El Niño event. We don't know what the triggering event is. It might just be a natural cycle that happens every couple of years, or it might be a system that is unstable enough that any slight random variations in the atmosphere and ocean patterns can trigger it. Hopefully we'll understand it better in the next couple decades, because it would be really nice to be able to predict an El Niño event before it starts. El Niño happens unpredictably every 2 to 7 years. The name El Niño means the boy in Spanish, and it's a reference to Christianity and the Christ child, because it sometimes caused warm currents off the coasts of Peru and Ecuador around Christmas time. Here's what happens. For reasons not fully understood, the trade winds over the Pacific Ocean weaken. Normally, the trade winds move water away from this coast of South America, which causes cooler, nutrient-rich water below to flow upward. When the trade winds weaken, This upwelling stops. The nutrients stop coming, and many fish either die or migrate. People, especially fishermen, in Ecuador and Peru, have a hard time. The warmer water temperatures make rainfall increase in Peru and Ecuador, leading to flooding and erosion. This can destroy crops as well as homes and transportation systems. El Niño also brings droughts to Indonesia and Australia and upsets weather patterns across large parts of the world. It can cause the jet stream to move farther south than normal, make areas in the northern US and Canada drier and warmer than normal, and make the southwestern US, such as California, wetter than normal. Or not. It's pretty chaotic and it's not the same every time. So, that's El Niño. But there's also La Niña. Dun dun dun! La Niña is what happens when the trade winds get stronger than normal. It's basically the opposite of El Niño, and it causes colder waters off the coast of Ecuador and Peru and different weather phenomena around the world. There's a natural but hard to predict oscillation between El Niño and La Niña and back every 2 to 7 years, though some years get a neutral phase that's neither of them, and El Niño occurs more frequently than La Niña. To recap, when the trade winds weaken, it makes waters in the eastern Pacific Ocean get warmer, fish there die, and all sorts of other weird weather things happen around the world. When the trade winds get stronger than normal, they are better able to move the warm water away from the coast of South America, leaving cooler water there, and a lot of different weird weather phenomena around the world. Oh, and one more thing I forgot to mention. El Niño makes the average surface temperature of Earth hotter. Normally, there's a lot of mixing in the Pacific Ocean that lets heat go deep down into the depths of the ocean. El Niño stops that from happening, letting the surface of the Earth get hotter. La Niña does the opposite, increasing mixing and letting surface waters be cooler than normal. The deep ocean provides an air conditioner for the whole climate system. El Niño turns it down, and La Niña turns it up. Not enough to offset global warming, but enough that it'll mess with your climate models if you don't take it into consideration. Okay, back to our overarching narrative. A rotating planet has a Coriolis effect and circulation cells that create trade winds near the equator. Something specific about Earth makes those trade winds in the Pacific weaken every couple of years in an event called El Niño. We don't know exactly what causes El Niño, so I don't know what advice to give you if you want to design a planet so that it doesn't have El Niño-like oscillations, except to look at what the Earth is like, the size and shape and distances between continents, etc., and don't do that. Okay, that's it for today. There's still so much of climate science that we haven't even touched on, but let's review what we have talked about. First, it's colder near the poles and warmer near the equator because of the angle the sunlight hits, more directly near the equator and at more of an angle near the poles. Second, it's colder the higher up a mountain you go because the air pressure is lower and air cools down when it moves to a lower pressure environment and expands. Mountains can block moisture from getting past, water has a temperature moderating effect, plants cool things down, ice and snow reflect a lot of sunlight and cool things down, and cities are hotter than their surroundings for a variety of reasons. Also, circulation cells make air move north to south. A spinning planet will have a Coriolis effect that makes air want to turn instead of going in a straight line, which produces things like trade winds near the equator. And if things are arranged in exactly the wrong way, you can get a weird climate oscillation like El Niño. And that's it. Now you know all about climate. How do you know what the weather is like at the top of a mountain? You climb it. I hope you enjoyed this episode. If so, consider following Ideas Worth Exploring on Spotify or Apple Podcasts or wherever you use to listen to it. And if you have the extra time, give it a rating. And come back next time for more science. Peace.
This has been Ideas Worth Exploring by Mark McDonald.